Okay, so this is a video lesson for 3.6, notes, the rational functions. And just to define what a rational function is, although you did learn this last year, so a lot of this is going to be familiar, only just a tiny bit's going to be new. To define it, a rational function is always in the form of p of x over q of x, where p of x and q of x are both polynomials. So we just reviewed polynomials, so we're going to use a lot of that information when we're graphing rationals. Okay, so let's consider the parent function. First off, as x approaches infinity, okay, what is 1 over infinity, or what is 1 over a really, really large number? That number is going to get closer to 0. Or the y value is going to get closer and closer to 0. The same thing is going to happen if you plug in a really large negative number. It's also going to be 0. What this is causing in the graph is the horizontal asymptote, meaning that we call this end behavior. Okay, we have a horizontal asymptote of y equals 0 because as x gets really, really large, y gets really, really small. And the same thing on the left behavior. Okay, we can't say what is f of 0, but we can say, well, what is happening as x approaches 0 from the right? So imagine a number that's just past 0 on the right, meaning a positive number. That's really, really small. What's 1 over like 0.00001? Well, it's a really large positive number. And if I did that same thing with a negative number, I would have negative infinity. And this is causing my vertical asymptote. So these things, asymptotes, they're kind of mysterious when you first learned them last year, but really all they are is just approaching behavior, either towards the ends or towards some number that has to be excluded from your domain. Okay? Now, in this particular problem, there are no x or y intercepts, but we know that f of 1 is 1. Okay, so my graph is going to do something like that. We know that f of negative 1 is also negative 1. And if you needed more values, you would just do a t-chart and plug them in. Okay, both my domain and my range are the numbers. X are all real numbers, but skipping over 0. Okay, so here we have some rules about asymptotes. These are going to change as we have more complicated rational functions. So x equals a is a vertical asymptote if as x approaches a from the right or the left, f of x is approaching infinity. And I'm going to put plus minus infinity because it could be positive or negative. Okay, in this particular case, f of a is undefined. This is another way that we know we have a vertical asymptote. Now there's another time when we might have f of a undefined, but it's not a vertical asymptote. That would be called a removable discontinuity or a hole. But this part right here is exclusive only to vertical asymptotes. Horizontal asymptotes are created for a different reason. So we have y equals b is a horizontal asymptote if as x is approaching positive or negative infinity, f of x is approaching this b value. It's leveling out. Okay? End behavior and horizontal asymptotes are essentially the same thing. That's because end behavior has to do with x approaching infinity or negative infinity, the far right or the far left. For polynomials, we didn't have horizontal asymptotes. We had where the f of x was approaching infinity or negative infinity. And that can happen for rationals, but for a lot of rationals, you have where it's approaching a horizontal line. So we'll explore that more with the examples. This is how you find the asymptotes. You may remember this from last year. The vertical asymptotes are the lines x equals a, okay, where a is a 0 of the denominator, okay? Another way to think about this is what you would have is, you know, your numerator, and then you would have x minus a. And again, you would not also have x minus a in the numerator. You just have it in the denominator, okay? If it were in both, that's going to cause a hole or a removable discontinuity. Okay, horizontal asymptotes, they follow 3 rules. Now this is, you just have cases. Now remember, degree is the highest exponent. So if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. This is just like the parent function. The degree of the numerator is 0. The degree of the denominator is 1. So if you forget about this, just think, okay, it's like the parent function. Sometimes I call these bottom heavy because the degree on the denominator is larger. All right, now if they're the same degree, which we're going to see in this first example that we do, then your horizontal asymptote, where I'm going to call this y equals a over b. All right, and this is the ratio of the leading coefficients. I'm going to do examples for all of these things, so if there's any questions, you can pick it up on the example or ask me a question in class. Now the third scenario was, well, what if this is what I sometimes call top-heavy? What if the numerator and the degree of the numerator is the larger one? Well, this is when we have a slant asymptote. This is when your asymptote is not a horizontal line, but a line with an actual slope. All right, and the only way to find this would be to do division, and normally we're going to have to do long division, but definitely we could use synthetic division on some problems at least. Okay, good thing about division, when we do this, we get to ignore the remainder. So it says you may have more than one vertical asymptotes, but you will only have one horizontal or slant. Okay, so find all asymptotes for this. Well, let's start with the horizontal since we've got this. It's multiplied out. It's in the easiest way possible to find it. The degree is the same, so we look at these two numbers, 3 over 2. Okay, now for our vertical asymptotes, what we need to do is factor. Okay, we really need to factor the numerator and the denominator. All right, now if I factor this numerator, I'm going to have 3x plus 1 times x minus 1. And if I factor the denominator, I'm going to have 2x minus 1 and x plus 2. Now you want to see if terms cancel. If they do, you need to do that right away, and that's what's going to cause a hole. Okay, but no terms cancel here, and the zeros of your denominator, or you could say set the denominator equal to 0, that's going to cause your vertical asymptote, and there are two here. We have one at x equals 1/2, and we have another one at x equals -2. Okay, and I'm just looking at the denominator there. All right, now let's actually go through a problem from start to finish. Okay, so again, this says this, what you're looking for first are the holes. Okay, and so a good place to start would be to factor if it's possible. Okay, so on this problem, the numerator is going to factor to 2x plus 1 times x minus 4. If you still have questions about factoring, please come to tutoring or ask me in class, because this is just a standard part of all of these problems at this point. Okay, now nothing cancels, so I don't have a hole in this problem. All right, but I do have some vertical asymptotes. I'm going to look at my denominator. I have a vertical asymptote at x equals -2, and I have a vertical asymptote at x equals 1. Okay, in terms of horizontal or slant, the degree is the same. So this is kind of like the one I just worked. I'm going to have a horizontal asymptote of y equals. Now for this one, it's easier to look at the top, 2 over 1, or y equals 2. All right, before I go any further, let's actually plot these asymptotes. And when I plot them, I'm also going to label them. And x equals 1. Always label your asymptotes, and y equals 2. Okay, now I'm going to switch up colors here, and what we're going to do is we're going to look at some easy points to find. The first one would be the x-intercepts. This is just like polynomials, where you're setting your y value equal to 0. You're just looking at the numerator. Write down as many notes as you need to so that you're going to be able to do this on your own. So just looking at the numerator, the 0 here would be -1/2, and I'm going to write this as a point, not just as a number. And then my second x-intercept would be 4, 0. Okay, y-intercepts are even easier to find. This is, and there's only going to be one, if there's going to be one at all. It's possible not to have one. If you set all the x's equal to 0, basically if you find f of 0, you would have -4 divided by -2, which would be +2. I do not think it is a good idea to memorize how to do this, how to do this, how to do this, how to do this, and it mean nothing. I want you to understand why you're doing this. This is how this is going to keep with you. All right, let's plot these points, and let's hope this is enough points so that then our graph is really easy to figure out what's happening. All right, so right off the bat, we have something that bothers some people. We have a point on an asymptote. You can definitely cross a horizontal asymptote, particularly in the middle. That happens a lot. Okay, you will never, though, cross a vertical asymptote. All right, and that's because the graph is undefined here. All right, you can't have a point where the graph is undefined. All right, what I like to do is I like to connect points. Now, I cannot connect these to this point over here because it's on the other side of a vertical asymptote. But what I can do is use the trend of the graph. Okay, what I'm doing is I'm letting the graph get closer and closer to these vertical asymptotes because that's what the graph does around asymptotes. This has to do with what I talked about at the very beginning of the lesson. All right. Now another thing to note is that you can't create any other x-intercepts where there aren't any. So this is how I knew here that I wasn't going to come back down because there are no other x-intercepts. I'm confident that I found the only two. All right, so when I'm looking at this point right here, the graph cannot cross the asymptote, so all it can do is kind of bend and get closer and closer and closer to it. Okay, up here, it is possible for this graph to cross this asymptote, but it is not going to. We know at the end behavior, it's definitely going to level out. All right. Notice that on this asymptote right here, this vertical asymptote, the graph was opposite. That has to do with because numbers just a little bit larger than 1 are going to create really big negative numbers. Numbers that are a little bit less than positive 1 are going to create positive numbers. It's just that at 1, it's undefined, and there's a behavior where it goes one way on one side of the number and the other way on the other side of the number. There is an exception to this rule, and that has to do with, it's not really called multiplicity, but let's say this x minus 1 had been squared. That actually would have changed many things in the graph, but one of them being the graph would have the same behavior. All right, so we'll get to that later though. For right now, let's just fill in the other obvious parts of the graph. All right, x equals -2, we're going to have an opposite effect. And I'm just going to graph the most simple case here. Now you can check all of this on your calculator. If you don't feel confident in these things, then you just go ahead and plug in as many points as you want. Okay? Be thinking about domain and range as well. That's not the focus of this lesson, but it is kind of where we're going with this. Okay, let's look at number 4. All right, so first thing, factor. All right, this factors into x minus 5 and x plus 1. All right, all over x minus 3. Nothing cancels, so there are no holes. So let's go ahead and write our asymptotes. Remember, vertical asymptotes are where the graph is undefined, so that would be at x equals 3. That's the only one in this case. Now in this particular problem, the degree of the numerator is larger, so I'm going to have a slant asymptote, and what I need to do is divide. All right, I'm going to do my work over here on the right. In this problem, I can do synthetic division, so why not do synthetic division? I could definitely do long division. It doesn't really matter. I'm going to be looking at my multiplied out version. It's just the factored version does not, we cannot do synthetic division or long division with it. All right, now at this point I can go ahead and stop because it doesn't matter what the remainder is. All you're looking at is this part right here, y equals x minus 1. That is your slant asymptote. Usually slant asymptotes are lines, but they definitely can be higher order polynomials. All right, so x equals 3. We're going to plot that asymptote and we're going to label it. All right. X minus 1, we've got a y-intercept of -1, we've got a slope of 1. All right, so right around in the middle you need to be accurate, but this is a sketch. But this is why we label these asymptotes so we know what they are. Okay, let's go ahead and find these points. First, let's find the x-intercepts. This is where we're looking for the zeros. And here I'm just looking for where the numerator equals 0, because 0 over some other number is still 0. So that's going to be 5, 0, and negative 1, 0. All right, so we plot those points, 5, 0, and negative 1, 0. And let's go ahead and find the y-intercept. This is where, y equals, or I'm sorry, this is where x equals 0. So if I plug in a 0 in for x, I get negative 5 over negative 3, which is positive 5/3. This is like 1 2/3, so I'm going to go ahead and plot that point right there. And again, if I have 2 points that are close to each other, I'm going to go ahead and connect them, and that's going to help me notice the trend of the graph. So here, my graph cannot cross that vertical asymptote, so it's just going to continue to get closer and closer. Here, same thing. All right, on the other side, hopefully this is obvious what's going to happen. Again, x equals 3. This is just a plain old vertical asymptote, so it's going to have a split behavior. By split, I mean on one side of the vertical asymptote, the graph is increasing. On the other side of the vertical asymptote, the graph is decreasing. This is a unique, well, it's not entirely unique, but this is a rational that has a domain where we just skip our one number, but this has a range of all real numbers. The last one did actually as well. That's why I kind of went back on my saying that it's unique. Some rationals have a very interesting range. It's very difficult to find, but sometimes you look out with the all real numbers ones. Okay, so number 5. All right, this one is mostly already factored for us. It looks like I could possibly factor this further. What do you think? Nope, not going to factor it further. Okay, so let's go ahead and just start finding the things that we know how to find. There are no holes because nothing cancels, but we have a vertical asymptote of x equals 2. And again, we're going to have a slant asymptote on this one. And if you notice, this is going to be a cubic, okay? And if you multiply all this out, I'm not going to spend a lot of time on that in this lesson, but if you multiply this numerator out, you get x cubed minus 2x squared plus 3. And again, you're either going to use synthetic division or long division to do this, to find out what the slant asymptote is, okay? I'm going to go ahead and use synthetic division again. I really like synthetic division. I think it's a lot easier, and I'm less likely to make mistakes. The only thing you have to consider is you have to put a 0 in for an x because the x term's canceled in that one. All right, so as I do my synthetic division, I notice that there's not a lot of terms. In fact, this is y equals x squared because we've got our remainder, our constant, our x, and then 1x squared. Okay, so that's interesting. This is new. You probably only toyed with this idea last year, but now we're going to actually do one. It's really not that bad, though. All right, let's go ahead and plot these asymptotes. X equals 2. Label it. Y equals x squared. Now, I'm going to try to go ahead and make this as accurate as I can with these points. The more accurate you make these asymptotes, the easier everything else will be. And I'm just using number squared and my knowledge of the parent function. All right, y equals x squared. Okay, now let's find those points. Okay, x-intercept. Okay, what you're going to do, same thing. One of them's obvious. Now, to look at the other one, you really would need to do quadratic formula on this second one to see, because you could just have x-intercepts that are irrational. All right, but in this particular case, if you were to do quadratic formula with this, it does create imaginary or complex x-intercept numbers, so there are no other x-intercepts. All right, y-intercept 0. Plugging in 0 for x, a little bit of number crunching, but here you get negative 3/2. Okay, so let's plot these points and let's see what we got. We got negative 1, 0, we got 0, negative 3/2. And again, I connect those two. Here, I know I'm going to do something like this. And then here, this is strange, but just follow the asymptote. All right, x equals 2, vertical asymptote. It splits the graph, and it splits that behavior. Now, I want to ask you something. Could I continue to go down all the way crossing the x-axis? No, because I don't have another x-intercept. So I'm going to have to come back up and just go towards the next intercept. All right, last example. Okay, here we have one that's, again, already factored, and something interesting happens on this that we haven't seen yet. We have a term cancel. This is going to cause a hole or a removable discontinuity. Now, the zero of that term, which is -2, that's going to be the x value of the hole. How you find the y value? Well, now that you've crossed off this term, it is to be seen no more. You're just going to find f of -2. You're going to plug -2 in for x here, here, and here. And when you do that, you get 5. Okay, you just got to do the number crunching. All right, and that is going to be a point on my graph. Okay, so go ahead and plot it. But it's going to be a hole, sorry. It's not really going to be a point, but it is, your graph will go right up to and then right on the other side of this hole. Okay, from here on out, this is just like any other one. So x equals 1 is my vertical asymptote. My slant asymptote is going to be another one where you have to do the division. All right, and I'm going to go ahead and just tell you what happens because I'd like to just focus on the graph on this one. All right, your x-intercept is going to be, you look at that factored form, we've got 3, 0, and we've got -5, 0. And my y-intercept is going to be 0, 15 by just plugging in 0 in for x's. If you have any questions about the numbers here, those are excellent questions to ask me in class. All right, now let's spend just the last part of this lesson focusing on this graph. Okay, x equals 1, vertical asymptote. Start up here at 3. Again, we've got a slope of 1. And right around the middle of this graph, you need to be as accurate as you can. Okay, this is a sketch, but if you lose too much accuracy on this line, it's going to affect what you think is supposed to be happening in the graph. All right. Okay, so again, this hole right here is going to act almost like a point. Okay, so when I'm plotting the other points, 3, 0, -5, 0, 0, 15, I am going to connect, and in this case it's 3. So this is not a point on my graph, but it is behaving like one. That's going to help me figure that part out. Again, x equals 1 splits the graph, and my behavior looks a little bit like this. I think you're going to find this year that this is just a little bit easier than you remember it being. We are going to spend a couple of days on this with 2 different notes and 2 different assignments because there are still some things we haven't discussed yet. Okay, bring your questions to class.